We have mechanical properties of solids. So in the mechanical properties of solids, we will see what are the different solids and what are their mechanical properties. So we observe that if you apply any force on a solid, so what are the different things that can happen with the solid? So as we know that the solids, they possess a definite shape and size. So if you apply any force on the solid gets deformed. So it may get deformed or it may even get broken up. So we will first study about the substances, how they get deformed here. Under this section, we will first observe that solids have definite shape and size. So if you apply some amount of force on the solids, so solids are the ones they will get deformed. Okay, there will be a change in the shape of the solids. But how long will the change last? The next question is how long the change will last. Suppose if you have a metal rod, so I take a metal rod over here, and suppose I put some weight on it. So on this metal rod, if I put some weight over here, so how long? Uh, of course, this metal rod will produce some elongation in the length of it will produce some change of length in this rod. So if initially it had some length L, after hanging the mass, it will have its new length L dash, and hence some extension must have has been produced. The extension is equal to L dash minus L, which is the extension produced. So we say that the solid or the metal rod, it has got deformed. So this is one of the deformation that is produced. The other deformation that can be there, so there is a deformation produced in the length. Now, how long deformation lasts? Okay. So this deformation will be there till you have applied the weight. By the application of this weight, you have some force which is acting downward. So due to the application of this weight, there is an extension produced. If you remove this, if you remove the force from here, so the extension that is produced, the extension will decrease. It will again, the substance or the solid will try to regain its original shape. Okay. So when it tries to regain its original shape, sometimes it may be able to regain its original shape. Sometimes it may not be able to regain its original shape. So how the substances are able to regain their original shapes? The reason being that the atoms, they are held together with the help of electromagnetic forces of attraction, or electrostatic forces of attraction are the ones which are holding the atoms together. So once if you are equilibrium being set up between the electromagnetic forces of the atoms and this force. So the electrostatic forces, they are trying to pull this mass in the upward direction. So in the upward direction, you will have some force, the same force F acting in the upward direction in this material. So in the material, there will be a force which is being set up in the upward direction, trying to pull this mass upward. And this force is trying to pull this mass in the downward direction. So here we observe that these two forces, they are acting in opposite direction. This force, the force that we had applied earlier, we call this as the applied force. This is the applied force that we have used. And this force that we are using, that has been set up between the molecules or the atoms. So this force is called as the restoring force. So we observe here that a restoring force has been set up in the material. Now so depending on the restoring forces, we define that how much will be the extension produced. Okay. Generally, the applied force, if you observe the applied force, so the applied forces should be equal to the restoring forces, but sometimes it may happen that the applied forces are greater. And if the applied forces are greater, it will be an unstable situation. And to overcome that situation, an extension will be produced in the spring. Sometimes the compression will be produced. So depending on that. Okay. So we define here a term, a stress, which will relate the amount of the restoring forces that we have used. So have you understood up to this much that why the solids can regain their original shapes? All the solids, they
Yes,
can
sir.
regain they can regain their original shapes because of the restoring forces which are being set up in their molecule. And the restoring forces will be there if you remove this, if you remove the substance, if you remove the applied force, so the substances will regain their original shape. So this was one example. In the similar way, we can have other examples. For example, suppose if you take an iron rod, something like this. You take an iron rod like this, and to this iron rod, you try to bend it. If you try to bend this iron rod from by applying some force over here. So if you are applying some force here and you are trying to bend it something like this. So you have bent it like this by applying some force. So in this situation, we observe that there is no change of length. Here the length has not changed, but rather its dimensions have changed. Still its dimensions, its orientation has changed. Okay. So in this case also, we will observe that there is a restoring force which is being set up. So in this case also, we will observe the restoring force set up. And hence, here we will observe that there is a shear strain that is produced. Such a strain that we observe we observe that there is no change in the length, but there is a bend in it. So here we observe that there is a shearing strain that is produced in this. Here we observed a longitudinal strain being produced. Longitudinal strain means there is a change of length. So when we observe a change of length, we call it as the longitudinal strain. When we observe a change in its shape, something like this, a bending like this, so this is a shearing strain. Okay. There is another type of strain which we call as the volumetric strain. So can you think of what is a volumetric strain? When there is a change in volume, if there is a change in volume, so we call that to be the volumetric strain. So volumetric strain will be there if there is a change in volume. We call that a volumetric strain. For example, suppose someone trying to compress a ball. You are trying to compress a balloon. So that is the strain that is produced or the change of volume is there. We call that to be the volumetric strain. Okay. So over there we observe volumetric strain. Here we have observed longitudinal strain, and here we have observed the shearing strain. Okay. Whenever we observe the volumetric strain is generally brought about by pressure. Okay. So we will see how to define the strain and how to define the stress, and then we'll move further. So how do we define stress? The stress, we define the stress as the force acting or the restoring force, the restoring force developed per unit area. So the restoring force developed per unit area, we call as the stress. So you can also say the normal restoring force. When you take the restoring force to be the normal means perpendicular to the surface. The restoring force developed per unit area normally. So you have the restoring force developed per unit area normally. We call this as stress. So stress is of different. You have a metric stress or a compressional stress. So in the normal stress, the force that is being developed is normal to the area. So that we call as the normal stress. First of all, we look at the stress. So stress can be written as force per unit area. Force per unit area. Now the different types of stress. You have your normal stress. Then you have shearing stress, this one is also called as tangential stress, also called tangential stress, and you have volumetric stress. You get here volumetric stress or compressional stress. The third one, it's called volumetric stress or compressional stress. Okay. So you have compressional stress. Now, the normal stress, it's taken as normal restoring force developed. It's the normal restoring force developed per unit volume. So the normal force per unit volume will be called as the normal stress. Shearing stress is the again here shearing stress. This is also taken as the force perpendicular to the surface. That is again the normal force. So you have the normal force or tangential force per unit area. This is a shearing stress. Then you find out the volumetric stress. The volumetric stress is given again as the force per unit area. This force is also perpendicular to the surface. So the force perpendicular by area, this here, it generally, when you are using the volumetric stress, so it acts on all the surfaces. It acts always perpendicular to the surface everywhere. So we call this as the compressional stress. So this stress, compressional stress, it tries to bring about a change in volume. Normal stress tries to bring about a change in length. So depending on the stress, you also have three types of strain. So the three types of strain, they can be listed in the same way. You have the normal strain, volumetric strain, and compressional strain, shearing strain. So you have strain, it is defined as change in dimension over original dimension. Change in dimension per unit original dimension. So the change in dimension per unit original dimension is called as strain. So as its dimension are the same, so the strain will not have any dimensions. So to find out the longitudinal strain, you need the change in length by per unit length. You can find here longitudinal strain. So the longitudinal strain, it's given as change in length per unit length. Okay. So change in length divided by original length. Since the change of length, it is proportional to original length also. So here it can be given as, I can write it as L dash minus L over L. This we call as the longitudinal strain. Longitudinal strain. In the similar way, we can find out the compressional strain or volumetric strain. So volumetric strain will be given as change in volume per unit original volume. So change in volume will be again final volume minus initial volume divided by the. Generally, volumetric strain is negative in nature. Since if you are applying the volumetric stress, so change in volume will be negative. You cannot apply a stress from the inside. You can apply a stress from the outside only. So generally, the volumetric strain is negative, except for the certain cases where we will observe that due to the gas pressure builds up inside and there we observe a positive volumetric strain. But in most of the cases, we will observe a negative volumetric strain. Okay. So this is also called compressional strain. It can be written as delta V, which is change in volume by original volume. Longitudinal strain can be written as delta L over original length. And you have the shearing strain. So shearing strain is something like, suppose if you have, let this be a wall, and on this wall you have a hanger, something like this. A hanger is put like this. Now on the hanger, if you attach some mass, hello, 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 हाँ 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 बोलो, हाँ बोलो, हेलो, हाँ बोलो.
Sir, you're on mute.
I think, am I audible now?
Yes, sir.
Okay. So if you have here some mass hanging from this, you will observe that there is a tilt being produced here. So suppose there is a tilt which is produced like this. So you have a tilt being produced here. So this is the tilt that is produced, and hence let's say there is an tilt of angle theta. Okay. So this tilt of angle theta can be measured as suppose it has come down by a distance x and it has its original length to be L. So this tilt that has been produced here, this tilt can be measured by tan theta. We can say that tan theta will be equal to x by L. Okay. So in this way, we can find out the shearing strength. So shearing strength is equal to theta. So here tan theta is almost equal to theta, and hence the shearing strength that will be produced will be equal to x by L. So I can put here shearing strength equal to x by L. This is the shearing strength that is produced, and hence we also call it to be equal to tan theta. So shearing strength is measured as tan theta. Okay. So these are the three stress and the three strain which are there. The normal stress, longitudinal normal stress, volumetric stress, and we have the shearing stress. In the similar way, you have here longitudinal strain, volumetric strain, and the shearing strain. Okay. The ratio of stress to strain. Okay. If you take the ratio of stress to strain, that is a constant. So this is also called as the Hooke's law. So as you have studied the Hooke's law is again here given in another way. You can say that the Hooke's law holds here. As per the Hooke's law, the stress is directly proportional to strain. So the stress applied is directly proportional to strain. As we have studied earlier, that force is directly proportional to the change in dimension. Okay, so it's the same thing presented in some other way. So we can write here that stress is directly proportional to strain, but within the elastic limit. This is the condition. Stress is directly proportional to strain within the elastic limit. Okay, so you can get here, if you stress by strain, or you can write stress is equal to some constant multiplied with strain, and hence you get from here stress by strain will be a constant. So we get here stress by strain as a constant. So depending on what stress and strain we are interested in. So suppose if you are interested in the longitudinal strain. So if you want to find out the longitudinal strain, so for that you must include your longitudinal stress or the normal stress. So if you take the same thing presented here, you say if you take the normal stress divided by normal strain, normal stress over normal strain. So normal stress over normal strain, this is equal to the Young's modulus. So this constant has a specific name. This constant is called a Young's modulus. So now you remember that Young's modulus is the same. It's the Hooke's law only. Okay, but only this constant has different names. If you are finding the normal strain and the normal stress, then the constant will be called a Young's modulus. Okay, if you are using the volumetric stress and compressional stress and volumetric strain, so then it is called as the bulk modulus. So if you have compressional stress, if you have compressional stress divided by volumetric strain, so compressional stress by volumetric strain, it is called as bulk modulus. Bulk modulus. I'll tell you some other name for this also. This is bulk modulus represented by the symbol K. Then you have the third one. It is called as the modulus of rigidity. So how they rigid the substances. The third is the modulus of rigidity, represented generally by the symbol eta. We call it modulus of rigidity. Modulus of rigidity. And this modulus of rigidity is given by, again, shearing stress or tangential stress. You can also call it as tangential stress over shearing strain. This is tangential stress over shearing strain. So you got all these moduli. They are depending on, they are the same constant, but depending on when you are studying about the normal stress, you will get the Young's modulus. If you are studying about the volumetric strain, it is called as the bulk modulus. And if you are getting the tangential stress and shearing strain, this is called as the modulus of rigidity. So these are the three modulus of elasticity which provide the strength of the substance. With these three, we are able to get the strength of the substance. Now there is another important in from this chapter. The most expected questions are from these three moduli. You can get a question from these modulus, and another question that is mostly expected in most of the exams is from the graph between stress and strain. So here we take a graph between stress and strain. Okay, so let's draw a graph between stress and strain. So here on the y-axis, I take this as the y-axis. Here I take as the x-axis. This is x, y, and I take here to be the stress. On the y-axis, I represent the stress. On the x-axis, I represent here the strain. So if you draw a curve between stress and strain for a material, you will get a straight line. So up to a certain value of the stress strain, you will get a straight line, something like this. So what it represents, I'll tell you that what this value, what this graph represent here. So it simply states that if you are finding stress to strain ratio, so that will be a constant. The graph is a straight line, so that means stress to strain ratio is a constant. Okay, and this is also called as the elastic limit. This is the point up to which your Hooke's law is being obeyed. So if you say yes, at this point, up to this point, your Hooke's law is being obeyed. After this point, if you increase the stress beyond this limit, so if you are increasing your stress beyond the limit, so the graph is no more a straight line and the graph becomes a curve. So from here you will observe a curve in the graph, something like this. Okay. So this point, let us mark this. This is a very important point. Let's mark this point as A. So the point A, it corresponds to the stress. Here the point A corresponds to the stress. Okay. So this point we get. Now this much is the stress which we call as the a limit up to which the Hooke's law is obeyed. Okay. Beyond this, the Hooke's law is not obeyed. After this, we observe that graph is not a straight line. Then we encounter a point which we call B. So let's mark another point B and let this point B be the limit of elasticity. This is called as the limit of elasticity. So we call this point, we say that A is the point up to which Hooke's law is obeyed. This is up to which where Hooke's law is obeyed. There is point B up to which we call as the elastic limit. Elastic limit means beyond this, if you apply some stress which is equal to this point B. So if you are getting stress which is equal to this point B, let this be point be represented by here. Let this be A dash and let this be B dash. So the stress that is equal to OB dash, that is the maximum stress it can withstand so that it can regain its original shape and size. So if you suppose if you use some stress equal to OB dash, so if you remove the stress, if you remove your stress, so the substance will regain its original shape. Okay. If you are removing the stress even from A, then also it will regain its original shape. After this point, if you increase your if you still go on increasing your stress, so your graph will no more be a straight line, and now the graph enters a region so that now it's a non-elastic limit. Non-elastic. So if you take any point in this, suppose I take a point C over here. So I mark any point C beyond B. Now if I say, suppose the stress corresponding to point this is C dash. So this is the stress. I represent this as C dash. Let this point be C. So if you have the stress equal to C dash, so at this point, the substance will not regain its original shape. Even if you remove all the deforming stress, the substance will not regain its original shape and it will develop a permanent state. So if you, something like this, if you are increasing your stress, it will follow this graph up to the point B. And if you remove the stress, so it will follow the graph backward also. Backward the same way, again come at O. But beyond this point B, if you have applied any stress, and even if you remove that stress, so it will not follow the same graph. It will not follow the same way. Rather, you will find here a permanent strain being developed. So you will find here a permanent strain even if you remove all the stress. So even if you remove all the stress, you will have a permanent strain equals to OO dash. That means it will not regain its original shape. So this is point C, it is beyond the elastic limit. Now, as you can see, after this point, after the point B, the graph is becoming more flattened. It's becoming more and more flattened like this. So the graph becomes almost flattened up to a certain limit. So you can see even by changing a small amount of stress beyond this point B, if you are changing even a small amount of stress, so corresponding to the small amount of change in stress, you have a large amount of change in strain. So the amount of change in strain that is provided is too large over here. Okay. So such a point is called as the yield point. We come across here a point, we can mark here a point D, which we call as the yield point. So this is our yield point. The wire eventually starts to flow here. Okay. So let this be point D, which we call as the yield point. Yield point. Here we observe that the graph is up at this point D. There is a large amount of strain being produced for even a small amount of change in stress. Okay. And even if you remove the stress, the wire will there will be it will continue to increase its strain. The graph starts coming down and it indicates that even if you are decreasing the stress, even if you lower the stress, then also there you will find extension being produced. Then also you will find extension, and at this point the wire will start developing constrictions in between them. The wire will develop constrictions in between them, which will lead to breaking of the wire. So eventually the wire will break at this point, and this point E is called as the break point. So the point E is called as the break point or fracture point. So you need to understand all these points clearly, because there is a question which will be asked from the graph. What is elastic limit? Then fracture point, yield point, all these are the questions which are asked from there. Okay, so after this, there is just one more concept in this chapter, then we can start with the question. And that is your, after this, you have another concept which we call as the elastic fatigue. So what is elastic fatigue? Sriyuta, remember about elastic fatigue?
No, sir.
Okay. So elastic fatigue is that, suppose we have studied here that within the elastic limit, if you are applying within the elastic limit, if you are applying the stress, so the substance can regain its original shape, right? But there is a concept that how long will it take for the substance to regain its original shape? In the beginning, the substance regains its original shape quickly, but as it is prone to more stress and strain, as it goes for continuous stress and strain. So a disease called elastic fatigue is developed. Fatigue means a disease. So now the time taken, elastic fatigue means time taken to regain original shape reduces or increases. Time taken to regain original shape reduces. So the substance cannot quickly regain its shape and size. Okay. So this is called as elastic fatigue. Overuse, this is caused because of use and disuse. Every time if you use it, so continuously it produces strain, then again regain its shape, again produces strain, again regain its shape. So in this way, if it come, if it is done too much of too many times, so it will develop a elastic fatigue. Now it will not be regaining its original shape in the same way with the same way. Okay. So this is the reason why we have the older bridges which are there. The older bridges, they are developed, they are declared unsafe. After certain time, the old bridges, they are declared unsafe because they cannot regain its original shape. Whatever material is used over there, that material cannot regain its original shape quickly, and hence it will be likely to prone to breakage. Suppose some vehicle passes through it, a strain is produced, and it does not regain its original shape. So till then another strain is produced. So in this way, more amount of strain will be produced, which will lead to the breaking or the collapsing of the bridges. Okay. So that is why bridges and buildings, after a certain amount of time, they are declared unsafe. That is because of the elastic fatigue. Okay, Srita. So I hope you have understood. Today we have completed this chapter. Now we just need to do some questions. Okay. So I'll be passing the questions in the group or either WeXL. So you can check over there. You can do these questions from there.
Okay, sir.
Okay. Try out to do them. Here are the questions. Uh, so as much questions as you can try out. Try doing this. If you are able to do all of them, so we'll move to the next topic. Fluid.
Okay,
There are
sir.
not much questions. There are just around, I think, 10 questions. Okay, Srita, bye.
Thank you, sir.